Thank you. I'm not used to holding a mic, so I might, hopefully my voice is pretty loud, so this should work. I understand this is the last talk, and everybody's waiting for drinks, so I'll try to do this at pace. I'm Shodhan. I have been working at Thoughtworks for a long time. I'm primarily been a technologist, so it's a bit weird to follow a talk about AI for conservation. That's a more exciting topic. So this is going to be a bit dry in comparison because it is about the IT industry. But the law of 2 feet applies. So if you feel there's something more interesting you want to go to, please do. I will not feel offended. I've spent the last few years focusing on large-scale modernization. When I say large-scale, we're talking about 20, 30, 40-year-old systems measured by 50 million lines of code, 20 million lines of code. So these are really, really large. They're generally the heart of these businesses, and they're really, really hard to modernize. I said I'm primarily a technologist, but I've also been spending a lot of time on Google Slides, so make what assumption you can about my technical or post-technical nature. So yeah, I'm going to talk about tackling legacy modernization using GenAI-powered solutions. There's a lot of hype around GenAI. Surprisingly, a lot of talks today also pointed out that analytical AI, as we now call it, is also equally powerful and probably has more applicability than GenAI. I'm going to focus on real experience that we've gained by using GenAI, just because this is the real world stories track. So what do I mean when I say modernization? I don't know how many of you are familiar with it. This is an industry term, but as with all industry terms and is common in the software industry, we sort of use it for our own meaning. So I try to think about modernization as is the change required to your software if it's not fit for purpose for you. So think about whether your technology is delivering the value that you want it to. If it's not, then you need to change it. Doesn't matter if it's 30-year-old COBOL or it is, I don't know, Java and microservices or whatever. If it's not delivering value, it needs to change. And that change typically is called modernization. There's a connotation of old and new in modernization, because the word is borrowed from the English language, and modern generally means more recent. But actually, modernization is about more dimensions than old and new. And I've listed some of them at the bottom right. Like there's definitely a cost angle to it, total cost of ownership. Everyone wants better total cost of ownership. There's a customer experience angle. Can you delight your customers, or is your product just generating a lot of complaints? Tech obsolescence, out-of-support systems are common in the tech industry. Time to market, can you be as competitive as your industry is? Can you compete well? And then given the large problem of talent, there's also talent attraction, retention sort of thing, right? It's easier to retain and attract talent when your systems are more fitness for purpose. So I'm going to talk about this problem, but specifically I just want to first talk about why it's hard. This is a McKinsey stat that 7 of 10 modernization programs fail. So that's not a statistic to be happy about. Why is this hard? There's something about quanta, right? Like legacy modernization is such a big problem. It's just hard to sort of do. In the old days, there was always a saying like, it's not rocket science, but today rockets are more easily launched than solving legacy modernization problems, right? So maybe we need to visit it. There's an expectation problem, right? These organizations have spent 20, 30 years spending millions of dollars building their business over years, and now they want a replacement in some months or maybe sometimes a year or not. There's an org structure problem. There's lots of silos, the governance models. They're not optimized for change. They're optimized for executing as is. There's a pace of change challenge. Technology industry moves the fastest amongst all other industries. If you were in the maker's talk, she was just saying how lawyers never assume that things are going to change at the pace of technology industry is changing, right? And of course, methodology. Like I won't go into this waterfall versus agile, but today still many of these programs run in a waterfall model in spite of a lot of evidence that is, right? So we were like, hey, what can we do about this? There's this new technology called GenAI, so it's a solution. We have this problem about legacy modernization. is there problem solution fitness, right? Like, and that's a key question. Generally, anything and everything that is on the hype cycle, everybody will say, oh, it can solve all the problems. But of course, we need to find good problem solution fit. And we were trying to see where that problem solution fit could happen for us, right? Now, this slide is not meant to be readable, right? So I don't expect you to read the slide. It's just trying to sort of bring into sort of your mind that modernization space is really, really large. The thing at the middle is like the value stream, and you can see a lot of sort of things that you need to do to actually modernize these large systems, right? So we had to choose a particular area of modernization to find this problem solution fitness, right? We couldn't, like, there's no one-click GenAI answer that, hey, here's the black box, click a button, and suddenly your sort of 30-year-old system is now modernized. So the area that we chose to begin with was understanding legacy systems, right? Because our hypothesis was, irrespective of what you're choosing to do, if you don't understand how your system works today, then you're sort of at a loss. No, it doesn't matter how whether you want to modernize or not, actually, it doesn't even matter, but you need to understand what your systems do. And why is it about systems? We have a saying in technology that the only source of truth is code. You might have documentation, but that might be stale. You might have people that say something, but the actual system might be doing something different, right? So really, it's about understanding the system. What type of things do people try to understand when they try to understand systems? And we sort of, like we've been doing this for a while, and so we said, actually, there's like maybe these 3 or 4 different categories in terms of how people try to understand this. There's how questions, right? Like, so questions about like, how is this particular feature implemented? How is this capability implemented? What questions? Some organizations don't know what their code or what their system is doing, right? Like, can you give me a town plan of your mainframe? And a lot of organizations don't have that. Where questions? Again, when dealing with large systems, it's not as it's not a human scale problem. You don't have the full system in your head. You need some aid in terms of navigating that source code, trying to find out where things are. And then what if questions, right? If I change this X thing, what is its impact, right? Legacy systems are famously called, it's very rare to find a well-designed legacy system by today's standards, right? They're big balls of mud. You try to sort of pull on one string and it pulls a zillion other things. So there are lots of reasons people want to ask these questions of legacy systems, right? They might be trying to decide whether they need to buy or replace a certain part of it. They might be trying to decide if there's a unique design element in your current sort of implementation that needs to be replicated. They might be trying to keep the lights on, or they might be trying to implement a regulatory change and trying to figure out, okay, what is the impact of doing this? So there are lots of reasons why they want to know this, but ultimately, these are the sort of categories or types of things that they generally want to know. And these are hard, right? Like, again, when dealing with a small system, a lot of this is easy. Go into your IDE, sort of find it, or if you've been dealing with the system for a few years, you become very familiar with it. With legacy systems, these are hard. Documentation is generally very limited or very stale. There's not a lot of testing around. Safety nets are poor. There are very few SMEs. Play sort of a superhero role. Like, there'll be 2 or 3 SMEs who know these systems inside out because they've been working on it for 20, 30 years, and they effectively become the central point of failure. There's decades of learned experience codified in your systems. There's layers and layers of change that's been put in there. I talked about big balls of mud, and the existing tooling is not great, right? Like, I often talk about this. Does it give you answers in a human-friendly way? There's a lot of like reverse engineering tooling available, and if you ask it how is something implemented, it gives you a flowchart of the code, right? Humans can't understand a flowchart that has got 100 nodes, 1,000 nodes in it, right? When I ask another human a question, I expect an answer that is at a good abstraction level, right? That I can understand. That's how humans understand things and learn things. And it's a continuous evolutionary process, right? I might ask a zoomed out question, then I might ask another zoomed in question, and so forth. And that improves my mental model for understanding these systems. So this is hard, and we didn't find good tools to sort of answer these questions. So we started developing our own sort of internal accelerator, right? It's called Code Concise right now, and it's basically in the space of code understanding and intelligence. And it's meant to be an asset for wherever we are working in this sort of space, right? And we didn't get it right the first time. We went through multiple iterations of implementation. I believe the iteration one was when I think GPT 3.5 Turbo had just launched, right? And at that time, we were like, well, great, we can use this to understand code. But generally, legacy code is huge, millions of lines of code. This only worked for snippets of code, right? So you basically had to find, I don't know, a paragraph of code that you wanted to understand, pass it on to a GPT-like model, and it would explain it to you. It was okay, but it wasn't still solving the problem we wanted to solve. So then we sort of pivoted again, and then this is the time when just the RAG papers had started coming out, and there was a lot of conversation about how RAG was reducing hallucinations and sort of helping with context window limits. Everybody here familiar with RAG, retrieval augmented generation? Yeah, okay, I can hear nods. If not, it's basically like adding a search index on top of LLM. And by moving from that iteration 1 to iteration 2, we figured out we could definitely answer the same question we were answering in iteration 1, right? Like, explain this code to me. But we could now also answer questions like, tell me how this concept is implemented, right? And so we've made a subtle shift of, in iteration 1, the human, the developer, if they want to know like how are permissions implemented, they have to first find the code that implements permissions and then ask the LLM like to explain that code. In iteration 2, you're sort of offloading that work also to the tool, right? So straight away you're asking, hey, tell me how permissions are implemented. It does the sort of heavy lifting of where is that code implemented. And again, in legacy systems, there's not one place. It'll have to go through a lot of different places and then abstract it up and give you a zoomed out, abstract human-friendly answer. But even with this, we were not satisfied because with RAG, the sort of search index that I talked about that's sort of in front of the LLM is basically treating code as English text, right? But we know code has more structure, and we were like, we are not using that structure well. So we then shifted to iteration 3, which is a combination of graphs and RAGs. So basically what we do is we build a graph representation of the whole code base. It's a bit more sophisticated model, and then apply RAG on top of it. This is also now called as graph RAG in the ecosystem. So similar concept to RAG, but uses graphs as one of the sort of key building blocks. So to summarize, this is now the current iteration of Code Concise. It has these 3 key pillars. Of course, there's the LLM side of it, which we are using for its strength of interpreting things, comprehending things, and helping to talk to a human as a human. There's the graph side of it, multi-decade-old technology, very solid, to help us create relationships about the code and make them available to LLMs. And there's ASTs, right? The abstract syntax tree, the ability to parse code and sort of provide those relationships to the graph. So what we found out is that LLM is just one part of the puzzle. You have to do a lot more engineering on the sides to sort of make this possible. So then back to sort of this, right? Like what questions, how questions, where questions, what if questions. How well could we answer these questions with this type of solution? I'd say pretty decent. This is a screenshot. I have a demo running on my laptop, but foundational models are very temperament in terms of their latency. So this is based on an open source COBOL repository. COBOL is a programming language in the mainframe world. Why am I talking about COBOL and mainframe? Because that's generally the hardest form of modernization. It's where this problem is hardest. If you solve for that, the hypothesis is you can solve for a lot of other types of legacy modernization. So this is a how question, right? How do validations work for credit card transactions in the system? I feel this is exactly the type of question I would ask another human. And whether the human would give me the same answer or not, this is a pretty good answer for a human to understand, right? So it's not giving you that 100-node flow chart to understand that question, although it can do that. It's giving you enough answer. And this is a chat interface, right? So you can go into more details. So for example, I can even ask it a more low-level how question, right? So can you explicitly talk about how account limit management works, right? So you can sort of ask the same how questions at multiple levels of zooms. And again, this goes back to my point, is this is how humans understand things, right? You ask a question, and the first question is probably very high level, very abstract, and then you ask more questions about more levels of detail, and that's how humans understand this system. And so this basically reduces the dependence on those SMEs, those 2 or 3 superhero figures that I talked about that are always there in terms of the people who run the business, but never available to answer you these questions, right? So now you can sort of straight away ask this technology the question. We also talked about this what question, right? Tell me what the system is doing, right? So this graph, again, it's not meant to be like you can understand how many nodes are there, but you can sort of see some coloring, right? So this is some bottom-up capability identification, right? So capability is a thing. It says there's strong definitions of what a business capability is, but loosely for this conversation, capability is trying to define what this code is doing, right? So those pink nodes that you see at the center are what are the 9 core capabilities that this sort of tool has detected in this code base, right? And then all the leaf nodes that you can see that are flowing from those pink or red nodes right in the center are classes or Java classes and Java methods that belong to that capability, right? Now, now suddenly you have a real town plan, not a town plan on a whiteboard, which is also useful, but now you have a real town plan of what capabilities does your system serve, right on there. The other sort of serendipitous, I can never remember that word, right? Serendipitous thing that we sort of achieved with this is when we started exploring these clusters, what we realized is some of, like let's take the blue nodes as an example. 2 of the blue nodes for 1 pink node happen to be different Java packages doing exactly the same thing, right? So this is another sort of characteristic of legacy systems. That there's generally a lot of duplication in those systems. And that's not syntactic duplication, right? It's not like it's exactly the same code, because that's easy to detect, right? There's loads of tools who can do that. This is more semantic duplications, right? It's roughly the same feature, but the code is being written a bit differently using some sort of different styles in different eras, maybe 5 years ago or 5 years later. And so suddenly we started finding duplicates across this sort of code base, right? So this was the what question. And then I guess I don't have an example to show you about the what if question, because that's something that we're just doing right now. But we're working with an aviation customer of ours who has one of the busiest SQL Server database in Europe. So it's a reservation database. So that's where you book your airline tickets and it reserves seats for you. And it's about, I would say, 2 million or 3 million lines of code. So not as complicated as the mainframe one I was talking about, but pretty complicated. 2 million, 3 million is also not a human scale problem, right? Like so, and there, the main problem we are trying to solve is if I change X, what else needs to change so that that change can happen? So imagine this aviation customer trying to change some rules around pricing or trying to change some rules around how seats can be grouped together when you buy, etc. Right? So the problem there to solve is like if I change X, what are the dependencies and what else needs to change? How real is this? I guess I put this in because a lot of GenAI conversations are about POCs. This is very real. We are working at a German automotive client. This particular mainframe is about 15 million lines of code. I know lines of code is not the best metric to judge, but it gives you an idea of how big or small is the tech estate we're talking about. And so mainframe modernization programs are really large, so multi-year, multi-hundreds of people working on it. So with this sort of solution that I talked about, we can potentially save 60,000 days of reverse engineering effort, right? So, and there's some detail on the slide that I'm not sort of going through, but effectively we automated 2/3 of the reverse engineering process at this client, right? So reverse engineering being the ability to understand what goes into the existing system so that the people who are writing the new system can make sure there's parity where parity is required. Sorry.
Can I ask a question?
Yes, please.
How do you know that there's like a concise giving you correct answers? Like,
Yeah.
how do you validate that it's as big as
So that's a great question, right? So I'll go into a little bit more detail about this to explain that. At this particular customer, they had a 6-week reverse engineering, call it phase, yeah? So 3 sprints, that's how they were working. For 4 weeks, 2 FTEs worked on creating a reverse engineering document for a module of the code. Module is a made-up term in this sort of context, so that's about 10,000 lines of code. So they were looking at the code, using some reverse engineering tools to create a document like, this is what the code does. And that would go to a subject matter expert, that superhero figure, who would say, yeah, this looks about right. I've been working on this for 15 years. That looks about right. That's how it worked, right? And so what we did is we automated creation of that document. Because like all of this knowledge exists in that graph that I was talking about. So we sort of extended this tool to automate creation of that document. So straight away you cut off those 4 weeks. And we have kept that last sprint of 2 weeks where they're iterating further, right? I mean, given the non-deterministic nature of GenAI, this will never be 100% accurate. To be fair, though, it's questionable whatever the humans generated would be 100% accurate. So it's a trade-off. I think we will always talk about trade-offs. But right now, the cost-value equation seems to be very attractive. And then, yeah, this is another one. So, cool. I'm almost on my last slide. 5 more minutes left. So this is a different context. And I sort of brought an example that's a bit more contrasting. So mainframe modernization being like COBOL, really hard in terms of modernization. This is not that crazy, so about 500,000 lines of code. In Java, more recent, like about 10 years old than 20 or 30 years old. Here, we used Code Concise to help with onboarding, right? So this particular client, one of their challenges was when they had to fix bugs, it would take them 3 to 4 weeks for their developers to find where to fix bugs, right? Like this, all the people who had written this code had gone away. So new developers were struggling to figure out like, okay, well, how do I figure out where to fix bugs? And again, back to that problem of legacy systems don't have great cohesion, right? Like it's not like you can just go to one place and fix it, right? There's lots of different places where things are duplicated. So what we did is we injected a new pair of developers. We are big believers in XP, so that's why pairing. We injected a new pair of developers here. We went back to their Jira and said, okay, what are the 3 or 6 big bugs that you fixed in the last month, right? We pulled them out, pulled their descriptions, etc., gave it to this new pair of developers, deployed Code Concise with it, and they were able to start finding fixes in 1 or 2 hours, right? And this was so successful that actually, while they were finding fixes to those old bugs, they also discovered a live issue and helped fix that as well, right? Like, so another sort of different use case, more about onboarding, more about how you can scale new developers to existing systems, but just to sort of emphasize the point that the kernel of the solution is the same, but it's sort of helping different things. And yeah, there's a lot more to be done, but I thought I'll just share this much. Yeah, thank you. And do I have time for questions? No? But actually, it's drinks time, so I'm sure.
Well, that's the eternal question, isn't it? So questions or drinks. Any questions from the room before we wrap up? All right, well, let's have a round of applause for Shodhan, please.